So, welcome everybody. It's a pleasure for me to start the first Hedy Lamarr lecture after the pandemic. And we have still a lot of people who are online and listen to us online, but I very much like to welcome everybody here who found its way into the academy. And I can tell you it's much better to be live than to be online. So, very warm welcome to everybody. And here at the Festsaal of the Academy, which was renovated in the last 2 years, so it's one of the very first events that is happening in the newly renovated hall. And also very special welcome to our speaker, Silke Weinfurtner from Nottingham. So the Hedy Lamarr lectures are part of the lecture series of the Academy of Sciences, the Academy Lectures, and which bring internationally renowned experts and guests to Vienna from very different fields of science, and to give public lectures to the colleagues and to the interesting scientific public. Also, I would like to remind everybody that we are still, in the midst of the pandemic, and try to remind everybody that, and ask everybody, please keep your masks on during the whole event and the lecture here. So thank you. But now to the day's Hedy Lamarr lecture. It's building on an idea from the Institute of Cooperative Media and Communication Studies, which dedicated the Hedy Lamarr lectures on the new effects of technology on society. So that Hedy Lamarr, as you may know, was an Austrian-American actress and inventor. She lived 1914 to 2000, and on one side, she's very famous for her movies. On the other side, she's very famous for everything you use every day, which is the frequency hopping encoding in mobile communication. So das Frequenzsprungverfahren, which she invented, and which is the basis of basically all mobile technology today. And in honor of her achievements, the Academy made these lectures, and also in honor of achievements, the Austrian Institute of Quantum Optics and Quantum Information here in Vienna named that telescope which they use for satellite communication, quantum communication to satellites, the Hedy Lamarr telescope. Now, let's go to our speaker today. Silke Weinfurtner is one of the leading experts in analog gravity, in making quantum simulation experiments of things like cosmological events and black holes. And she's professor of theoretical physics and experimental physics. So I think there are very few people who can have both cards. And she sits officially in the mathematics department, but has all her labs in the physics department. So basically, and she just told me that you're taking over the complete physics department with your labs, right? Yeah. So she leads one of the big quantum simulation for fundamental physics networks in the UK. That's a set of programs that were set up in the UK to study fundamental physics by quantum simulations. And the network that she leads deals with black holes and with parts of the early universe. And she will tell you parts of what people do in there. She also holds 2 very prestigious fellowships at the Royal Society Fellowship, and she has one of the Liverpool Trust Research Fellowships. These are fellowships that are given out 1 or one or two every 5 years, 3 or 5 years for physics in the UK. So it's a very, very prestigious fellowship that's given usually for all the different sciences, but physics usually gets it once every few years, and she holds one of those fellowships. She's also a visiting fellow at the Perimeter Institute in Canada, and there's many other positions that she had. So she was originally a theorist, but then did the first successful experiment of making an analog black hole and making a measurement of analog Hawking radiation when she joined Bill Unruh, who's also a theorist as a postdoc, when they built up the experiment there, which is now 15 years ago or something like that, or 20 years ago, something like that.
Not quite 20.
Not quite. So between 15 and 20 or something like that, yes. And from there she developed, so to speak, all her scientific endeavor. She has many patents. Remember, as a theorist, she has many patents for technologies that you need to measure this type of subtle effects, which you will see. And her basically goal is really to understand by analog simulations physics that I cannot really build in the lab. I cannot take a black hole and put it somewhere and do it, or cannot find out inflation or something like that. I cannot do it because, you know, we can observe it, but we cannot experiment with it. But in analog simulators, the hope is to be able to experiment with that, and that's what Silke will tell us today. It's this quantum simulation of early universe and the black hole physics, please.
Thank you, Jörg.
And there will be questions from the outside, and I will get them, and I can then also ask them. Okay.
So thank you, Jörg, for the generous introduction. And in general, I want to thank the organizers for having me here today. It's a great honor to take part in the Helium lecture series. Right. So when preparing this talk, I thought about the audience, and I thought about Vienna, and I thought, well, it's a Tuesday night at 6 p.m. in Vienna, and I think many of you face the dilemma. Should you be going for a nice glass of wine in a restaurant and socialize with friends, particularly today, so lovely weather, or should I come here, sit indoors, wearing a mask, and talk about black holes? So I'd like to thank you for making the choice of joining me here today. But then what this talk is about is, what can you do with a glass of wine? And the first thing we're going to do with a glass of wine, we're going to put a black hole inside. So if we look at that slide, it's a very simple slide. It's a glass of wine plus black hole, and then that's what we're getting. So this is what you might have in mind, but what that really is just some vortex flow. And to be honest, you're almost there. And this is what the first part of the talk is about. What kind of black hole physics can you get out of a configuration like that? And what has that to do really with black hole physics? Okay, so before we get into the details, and I've been told this is a general public talk, so I understand that many of you are scientists, so apologies, stay with me. There are some very basic slides. What's a black hole? What's so special about it? And how can we think of this being, appearing in a hydrodynamical system in a fluid flow? So our current understanding of gravity, general relativity, thinks of gravitational field as a space-time geometry. And this space-time geometry, here depicted as this sort of blue sheet, that gets deformed if you have a heavy object, a star. And so the gravitational field, really you should think of this deformed or curved space-time geometry, the space-time fabric, if you want to. And the heavier, the denser the object is, your star, the more this gets deformed. Now, stars eventually have to undergo a gravitational collapse. And then depending how heavy your star is, it may just condense to some very dense star or neutron star, or sometimes this gravitational collapse cannot be prevented, and it collapses further. And all that is left behind is basically a hole or a puncture in the space-time fabric. And how do we understand it? So here, this is this depiction of a black hole. So a star, a heavy star, collapsed from the black hole that created sort of this gravitational trench. But the difference between that side here on the left and the right-hand side is that this is a never-ending trench in the space-time fabric. And then there are weird things going on. You can define an area inside, and if you pass that area, nothing can escape, not even light. And if you really wonder about what's happening deep inside, our current belief is that there will be a space-time singularity. Okay, so these are these very mystical black holes. And what is really interesting is because you have this strong gravitational pullback around black holes, and anything that moves around, including light, gets deformed and gets deflected and may be trapped. And so somehow this seems like a very complicated, abstract concept. And so in 1980, Bill Unruh started thinking of how to explain black holes with a simple analogy. And at first, so what he had in mind, he wanted to look at waterfalls. Can I explain a black hole by thinking about waterfalls? And when he was talking about waterfalls, he was really thinking about sound waves that propagate in the bulk of the fluid flow. And so how does this work? So let's just assume for purely hypothetical reason, I have a purely hypothetical Gedanken experiment. I have a fluid flow that if I have it at rest, so there's no flow, water is just standing, and I look at sound waves, how they propagate. I have a little speaker inside the fluid flow, and I send some sound waves out. And then these different rings here, the different colors, show how the sound waves propagate sort of through the fluid flow in, equally fast in all directions. Now, suppose you are switching on the background flow, getting closer to the edge of the waterfall, and then I have a little speaker there, and I look how sound waves get excited. Then, of course, sound waves can propagate faster with the flow as they can propagate against it. So if we look at this little dot up here, sending out sound waves, we can see it again. You can see that the sound waves have a harder time to propagate upstream than they're propagating downstream. Now, back to our Gedanken experiment. What if I speed this fluid flow up to become supersonic? What does that mean? That the fluid flow exceeds the sound wave speed in that system. And so if that's happening, and now I create a little perturbation here, what I see is that all the sound waves, they're going downstreams. Nothing can propagate upstream. Now, if I already conceptually think about that, that defines two different regions in my fluid flow. On the one hand here, we have this subsonic region, where sound wave can propagate both ways, upstream and downstream. And then I have a region where sound waves are just trapped and they're getting swapped downstream. The area in between you could define as the acoustic surface or acoustic horizon in the system. Okay, so this is a nice way of understanding light propagation around black hole. This is what happens to light and why everything gets trapped. Now it turns out, and here I have to apologize, there are a few equations in there, but that's more for psychological reasons. For the ones here who are scientists as well, they would like to see an equation, and if I had to choose my equations wisely, this one I needed. Okay, so what is this about? So here we have a wave equation. That's a second order partial differential equation. Very difficult, but why is it so important? That wave equation occurs in a lot of physics. So for material waves, seismic waves, fluid waves, acoustic waves, and also for light waves. So it describes us how waves propagate in a variety of different media. Now you could say, what happened to this wave propagation if I'm nearby a black hole or a curved space-time geometry. And so there is a simple way of doing this in an ad hoc way. And that is simply to say, well, there's a trick of rewriting this wave equation here in a compact way. Now, it's not so important to understand the full mathematics behind, but one of the things you have to do, and you have to understand in this context here, is that if you, the way to write it in this compact way, you introduce a Minkowski space-time geometry, flat space-time geometry. Okay? How space-time behaves in the absence of any matter around. And so here now what becomes very visible, it becomes how my fields couple to this space-time geometry. And once you're at that point, you could say, well, let me do some sort of minimal replacement. Let me just replace this flat space-time geometry with a general curved space-time geometry. And so I take a metric tensor, a space-time geometry that describes a black hole. I put this in that equation, and then I can see, for example, how light propagates in the vicinity of a black hole. There is a lot to talk about, but that's not the subject of today's talk. So why is that interesting? So this kind of line of research we call field theory, classical and quantum field theory in curved spacetimes. So that sort of sets a mathematical framework, a set of equations we are studying to see how fields, how perturbations behave around black holes. And what's happening is, if you look at perturbations, fields, matter fields, propagating around black holes or in general in curved space-time geometry, what you get is what I would call wonderfully bizarre physical processes, new physics emerging. And to give you two prominent examples for that, which I will not be talking about today, but the one probably everyone knows about is the Hawking radiation. So a black hole, classically, can only absorb things. It can only grow. It can only accumulate more and more mass. But if you look at quantum fields around a black hole, then Stephen Hawking discovered that actually this black hole, through a quantum process dubbed Hawking radiation, can emit a thermal bath of photons given off of the black hole. And that process creates this thermal radiation, but it also creates a counterpart that goes inside the black hole, that falls into the black hole, and that has what we call a negative energy, and it reduces the mass of the black hole. So that's the Hawking process. And then you also have other effects. If you look at rotating black holes, there is a process called superradiance and Penrose process that tells you how a black hole can lose its angular momentum, how it can interact with the environment, with the fields to spin off. So these are just two examples, but these are really important processes in the sense that they tell you how the black hole really evolves. And so both of these things, for example, are very hard to impossible to observe in nature. And what we've done in the past, we set up experiments, Jörg already mentioned this at the beginning, to look at Hawking radiation and analog gravity system, and also superradiance. And so these analog gravity simulators, they exhibit the same sort of effective field theory equations of motions, and therefore, if we do everything correctly, they should lead to the same processes. So this is the basic idea. You now have a class of systems that follow the same mathematics, and now we can test how our calculations pan out, how we are solving this class of mathematical equations, and if our approximations make any sense. Right, and here we are at this. So what are these analog gravity systems? As I said already, a class of laboratory systems. And what you really have, you have small fluctuation that can be classical or quantum depending on what system you're dealing with. And what they all have in common, their equations of motions have the same equations as fields in curved spacetimes. So this is where this analogy comes. It's beyond a simple Gedanken experiment, beyond explaining how light can be trapped in black holes. Okay, so that brings me back to the promise, I said we're going to talk about what can you do with a glass of wine. So a glass of wine is actually a very interesting physical system. And it is so because you're not only looking at the fluid flow in the bulk, where of course you can excite sound waves, but it has this wonderful extra feature. It actually has air on top, and so you have an air-fluid interface. And what I'm interested in is this two-fluid interface, which has completely different physics. And in the sense that best way to explain it, why is it so interesting, if you look at sound waves in the bulk of the fluid, which are also there, the sound waves in the fluid have roughly 1,500 meters per second. The interface waves, which form on top, they have a very different speed. And they depend on the height of the fluid flow, and you can tune them at will by changing the height, and usually you operate in about meters per second. So they're much, much slower. And if you remember what we said, these acoustic or sonic horizons or effective horizons, they form when the fluid flow exceeds the propagation speed of your perturbation. So since the perturbation is much slower, it's easier to manipulate a physical system, a laboratory system, to set up interesting horizon structures. Right. Now, hydrodynamic rotating black hole. Let's start with this. So how do we set up an analog rotating black hole? And in order to understand that, we need to, in general, understand how why rotating black holes are so interesting, and that's generally translate why black holes are so interesting. And black holes are fantastically weird in the following sense. So when we talk about special relativity, we need three notions of time: the future, the right now, and the past. And because of this finiteness of the speed of light with which we are exchanging signals, we can always define a future light cone, as we call it, in our entire future. All of the events that we can have access to, they lie in the future light cone. And then the things in the past, everything that happens in the past is in our past light cone. So it divides up your future and your past. Now what's happening is when you come close to a rotating black hole, these light cones, your notion of the future and the past, or the future, is changing. And what is happening is when you come too close to a rotating black hole, your light cones start to tilt. And what this means here, if you look at the future light cones inside here, they tilt in the way that they are showing in their direction of rotation. So this is a counterclockwise rotating black hole, and what this means, if you enter this ergo surface, this ergo region, if you cross the ergo surface, you experience frame dragging, and you get dragged along with your space-time fabric. And then if you go further in and you cross an event horizon, what is happening is now that your light cone gets tilted even further. And what's happening is space and time gets interchanged, and now your time and space interchange means now your future points towards the singularity, the center of the black hole, which means your future is to fall unavoidably into this black hole, and you can never escape. And so this is the weird thing that happens around black holes. And the same thing you can set up in an analog black hole or a hydrodynamic fluid flow. So how can we find notions like the black hole horizon and the ergo surface? Okay, so the physical system we are considering are stationary draining vortex flows. And we are looking at the air-water interface, and we're looking at a two-dimensional velocity field. So we have a radial direction of the flow, and we have an angular direction. And then you can define the ergo surface, the black hole horizon first, is when the radial velocity component exceeds the ripple speed of the surface waves in the system. And then you can say this ergo surface lies when the total velocity, the radial squared plus the angular velocity squared, is equal to the speed of the ripple squared. So this is how you get these two notions, And if you look at waves interacting with such a vortex flow, you get the same thing as frame dragging and trapped regions. This is the analogy, and you can put this onto a rigorous footing. You can derive the equation of motions for your little ripples on the free surface, and you can show that you can introduce an effective space-time geometry, and you have then a wave equation on an effective curved space-time geometry. That's a lot of math, so let's the math behind us now, and let's focus on some experimental results. So this is a picture taken of the black hole laboratory at the University of Nottingham. This is a bit warped. It's not that warped because it's a curved spacetime. It's just that is the lens of the camera to take it all on one shot. So it's 3 meters long, 1 meter 50 wide, and half a meter high. There is a drain hole in the center, and the water is being fed in a way so that the whole flow gets an angular momentum. Then we set up some detection methods, which I'm going to talk about later again. Okay, so now that's the setup, a very basic, easy setup. It's almost like your bathtub at home, just that the plug has to be in the center. Now what we're going to do now, we have a wave machine on one end, and we're sending in coherent waves, just these wave fronts, which are coming out of the wave machine at a fixed frequency. And then we record these waves over time. And all we did here is we filtered the data to only show what's happened at the stimulated frequency band, so that we see fully and can isolate the rest from the wave we're sending in. And what you're seeing is here that this wave interacts with the vortex flow, and you get this funny pattern happening here. Right. And what we're going to do next, we're going to investigate how this pattern comes about and what has it to do with some notions of geometry associated to the effective curved spacetime geometry. Right. Okay, so the first thing we want to do is, we know that when you're looking at a black hole, you get light bending. There was this famous Event Horizon telescope effort taking pictures of black holes and showing how light is being bent around a black hole. So since this is an analog black hole, we also expect some analog light bending in the system. And so how could we understand light bending in a simple way? This is a very rudimentary simulation. We did this very early on, but I think it shows nicely how waves are being affected in such a system. So here we have, you could think of individual points launching here with a certain impact parameter, and I'm sending it into the vortex flow. Or you could just say one wavefront as it interacts with your fluid flow. And what you can see is that the wavefronts on the top and the bottom, they get deflected so much that they self-interfere. And this is exactly what light bending does for you. It tells you that in curved spacetime, things have to work on, you have to replace your straight lines with geodesics. And any object, free-falling object, has to follow this geodesics. And so if we then launch a trail of wavefronts and send them into the vortex flow, each one of them, because they experience an effective curved spacetime geometry, they experience frame dragging, all these things, you see that you get this funny wave pattern simply as a matter of an interference, self-interference of the top and the bottom of the wave. Right, and then what you can do, you can take your experimental result and you can plot on top of it the predicted wavefronts using all the tools and techniques developed for black holes, and you can see that yes, indeed, there is a very good agreement. Okay, now that brings me to another black hole feature, which is called black hole ringdown. And so black hole ringdown is something that has been observed through the gravitational wave, the LIGO collaboration. And what this is about, so one way to see this black hole ringdown is to say, I have two black holes and they start merging, they come closer, orbiting each other, and at some point they form a single black hole. And then when the single black hole is formed, the story is not yet done. And what does it mean the story is not yet done? While the black hole is merging and getting closer, it sends off these gravitational waves. And when the black hole has formed and formed a single black hole, the black hole is not quite done. It still shines off some radiation, and this is called the black hole ring down part of it, where the newly formed black hole has some rest energy left, and it gives that off through this black hole ring down. Okay, so how can we find and how can we understand these black hole ring down modes, and how can we find them in our analog gravity system, in our fluid flow? So what we're doing again here, we're launching geodesics, which we're launching little particles, think of little point particles moving along here, and I'm starting them with a certain impact parameter on this slice, and I'm sending them towards your vortex flow or rotating black hole. And what you see is, so depending on where you are here, you either end up in a black hole or you can escape, as we call, to infinity. So if you're launched off here, you see these blue rays, they can escape. But if you start somewhere over here, you will fall into the black hole. Now, because this analog black hole here is counterclockwise rotating, it goes around like that, which means that these guys here on the lower part, they are sending counter-rotating. And what means here is you have this counter-rotating, they enter the black hole in a counter-rotating manner, and the difference between the ones that can escape to infinity and the ones that fall inside, the difference between is what we call the circular orbit. And the circular orbit means if you were to take a point particle and put it on that orbit, it would just orbit forever around. It would neither escape or fall into the black hole. That's not the same case with a wave. A wave will slowly leak out. And so what you get due to this equilibrium points in the radial direction, or these critical points in the Hamiltonian, which we dub as light ring, what you get because of this is you get this ring down frequency, which has a real part that's related to the circular orbit, and it has an imaginary part. It exponentially decays. And this imaginary part depends on the boundary condition. So we have a black hole in a box, so this is harder to see, but the real part is there, and the moment these light rings modes are a robust concept. So now there are many ways to see it. One way would be to just send a train of waves, stop it, and see if something remains that hovers, stays on the circular orbit, and slowly leaks out. That would be one way. This is a simulation. As you see this spiral here you're getting at the end, this is simply this ring down mode. Just to see it again, so I send a wave over because I stopped this wave, but something is trapped, and that's what's trapped, is slowly leaking out. That's a ring down mode. That's all it is. But of course, when you do this in an experiment, you send waves in and stop, you eject a big signal. So we had problems with the boundary conditions because we have a partially reflective boundary condition, and this messed up a bit the analysis. But the beauty of this black hole ring down is that you can actually excite, there are many ways to excite that. There are the end product of a black hole merger, or the end product of, like, if you would send a Gaussian wave over it. But you can also simply get them in any way by perturbing the system. And this is what we did. We took a vortex flow and we took it out of its equilibrium. And then we let it relax back. And we wanted to see if this noise, which is already kind of characteristic counter-rotating noise here, if this actually is equivalent to the analog black hole ring down. And then what you can do is you can do a frequency analysis to see which frequency modes are populated. And then what we can do, we can also see, we can dissect this signal further. We can say, well, here there's a clear prediction of which modes should be excited, in the sense I'm looking at modes that are waves that are fully going around in the same direction of the black hole, a positive, what we say, azimuthal number, or a negative one. And an azimuthal number is basically has to be a discrete integer, and that's simply because if a wave would go once around in the system, around a vortex flow, it has to be continuous, so you can only fit full wavelengths. And how many wavelengths you fit is given through these azimuthal modes. So if you have m equal 1, you know it's a wave that has one wavelength that they can fit, that is co-rotating with a vortex flow. And when we do this, what you can do, you can plot the azimuthal numbers and you can plot the frequency. The black line is the theory, the green dots with the error bars is our analysis. And so what you see here is that indeed, naturally, this vortex flow, if perturbed, actually excite these modes. So it was predicted that you should have these modes, but since they are excited from a non-equilibrium process, it was not clear how easy it is to actually excite them. Right, and you say, okay, there was a quantum in the title, and that's all classical fluid flow, and that's true. And so let's talk about quantum physics. Let's try to go a bit beyond. So what about quantum black hole process? So we know that perturbed black holes, they emit these characteristic waves, right? These ring-down modes. We also say that these ring-down modes are naturally excited in these analog systems, or easily excited. And the question is, can we now take this classical system and translate it to the quantum domain? So how would we do this? So the first thing is, we don't have a theory for a quantum black hole. We have some quantum gravity theories and perhaps some ideas of what should happen, but generally speaking, we don't know how a quantum black hole should behave. So, however, it would be very unusual if a quantum black hole would not exhibit quantized vibrational degrees of freedom. So one assumption could be, what if I take an angular black hole that has a discretized angular momentum, a discretized circulation, which is a quantum feature? What if I can set up and probe this black hole ring down around vortex flows that exhibit such a behavior? So that's sort of the only idea, is that, or a conjecture, a quantum black hole should in some domain exhibit quantized circulation or quantized angular momentum. So in order to do this, you need to replace your fluid flow with a superfluid flow. And what does this mean? Superfluid helium is my superfluid of choice. And it is a particular fluid that doesn't solidify when you cool it down to very low temperatures. And very low temperatures here, we're talking minus 270 degrees Celsius. And what you have here is a transition point. And what happens beyond this transition point, your fluid, in a simplified way, becomes a two-fluid system. It has a normal and a superfluid component. And what does it mean is, initially everything is in the normal component, but the normal component goes to zero. That's the ratio of normal component density versus the total density. And when you go down to zero, where does this component go? It becomes a superfluid component. So by decreasing the temperature further, you create this superfluid. And this superfluid has some very peculiar properties. So it has a macroscopic quantum decoherence, and that leads to a fluid with zero viscosity, very high thermal conductivity, and quantized vortices. And what's interesting, if I take a superfluid helium, put it in a bucket and rotate it, and put myself, look from the bucket, maybe co-rotate with the bucket, that's what the simulation is, I will see a following situation seeing. So the rotation creates these little holes in here. And these little holes is a rotating states of the superfluid that consist of quantized vortices. And they form this nice lattice here. And so what it means is that the vortex strength in these systems is quantized. And so the superfluid can only spin in certain values. And so this is the reason why to go to superfluids. And in order to do that, of course, you have to change experimentation completely. And so here we started this new lab, Quantum Simulators for Fundamental Physics Laboratory at University of Nottingham. Okay, so who tells you that in a system like that, if you have this discrete vorticity or this discrete angular momentum, who tells you that you would still get any notion of ring down? So we did a simulation. The simulations here are not for helium, they are for a pure superfluid, a Bose-Einstein condensate, weakly interacting superfluid, using standard Cross-Peter-Yevsky approach and simulations to solve for this system. And what we're doing is we're stacking a lot of angular momentum in the center here. There's no drain. It's just a macroscopic vortex cluster. and then we run the simulation with some damping, which leads to the spread of that vortex cluster. And what we are having here, we can define this outer ring here is this light ring in the system. We can calculate what there sits, or the sound ring would be a better way to describe it. And what you see, sort of, sees better on my screen, but you see it here also on the display, that you see that there are a lot of waves being excited. And one thing which we did, we looked in this noise to see if this noise has any, is not just random noise, but if it can actually be described using black hole perturbation theory. And again, we have a prediction for this azimuttal mode number and which frequency we expect it to occur. And what we see that if we look at a certain frequency, and these violin plots tell you the amplitude, where's the maximum amplitude in the noise, we can clearly see that there's a lot of noise generation, exactly which has the characteristics of these black hole ring down modes. So this is just sort of to convince yourself, okay, so if I take a system, a quantum system, this ring down is still present, but of course this is not ultimately where we want to run this simulation. It's just that it's good that it's not completely gone by switching on discretization. Okay, so again, the experiments we want to carry out are not quite as simple as that, as a superfluid which is just rotating. What we want to set up is a superfluid that has internal circulation. So it has a drain, there's a superfluid, there's a drain, and it gets recirculated, and you set up a superfluid draining bus-step vortex flow. So since of last year, we managed to set up such a flow. And how does it look like now? So I don't know if you can see, but here there's a vortex flow. So this is down below 2 Kelvin. This is a superfluid helium bus-step vortex flow. And what we are doing at the moment, we're trying to characterize this superfluid flow because it has some very interesting physics, and it's one of the systems that has been overlooked. So we expect that much interesting will come out about it to understand how vortices will arrange themselves, and you can set up a variety of different conditions by simply modify the inlet conditions. So here, while of course we are interested in the ripples on the free surface, it's very hard to see here because helium has a very low refractive index. You can barely here see that there's some excitation. This is what we are after. What we also want to do is to study this vortex flow and understand it better. Okay, so a little bit of quantum, but then also this is the Helium lecture series or event series, and in some sense, of course, there was this fantastic story about this famous actor who is this self-taught inventor. So I felt like I should say a few things about, is there some commercialization, is there something coming out of this research which is of more practical nature, which sort of would justify why I'm here today. And what I can say is, how do we sense these hydrodynamic black holes becomes a problem of how do we measure fluid interfaces, and fluid interfaces are hard to measure. So the first thing we have been doing for the black hole experiment, the hydrodynamic black hole experiment, looking at air-water interfaces, we developed this sensor together with the company N-Shape. It's based in Germany, and it has, of course, in German a more serious, I'm calling it the ripple catcher, but the official method is called Verfahren zur 3D-Vermessung von Flüssigkeiten und Gelen. So it's a method to measure 3D measurement of fluids and gels. So how does this work? This sensor here, which is a standalone device, has a projector in the middle here. And what it does, it projects a random pattern of blue light. And what we do, we took the water, put some fluorescent dye in there. So fluorescent dye is an orangey powder. If you put it into the water, it converts, it becomes green because it takes the blue light of the spectrum and converts it into green. And so when you do this, there are two modus of operandi in this detection method schemas. One is that you can simply collect all the data and then do data analysis and present it. For example, you can create this nice point clouds which we are creating in was on my slides before. But there's another operation modus which is a live reconstruction. So, and the way this sensor works, I should have said that, apologies. So you project this pattern, and then you take 2 images from the right and the left here in the sensor. They're cameras. Each camera takes 800 frames per second, and then you get, because of little ripples, they distort that pattern you are projecting. And by having a stereo imaging, you can look at correlation measures and reconstruct that signal. And that gives you these point clouds. But we also can have a light reconstruction, so this whole sensor comes with a heavy workstation because you need to transfer and process these images very quickly so that you can see a live reconstruction on your screen. Right? So clearly, when we go to superfluid helium, we can't put some dye in there. Would be lovely, can't do it. Also, the method is not precise enough. So when it comes to superfluid helium, we need to do something different. And it all boils down to the same thing, which I think is most nicely explained in the paper, which I wrote with Jörg and Sebastian, who are here today. And that is, what we are doing is we're transferring the information we're interested, which are the fluctuation on the interface or 2D surfaces. This could be in ultra-cold atoms, 2-dimensional ultra-cold atoms, Bose-Einstein condensates, or here in the helium interfaces. We're transferring these fluctuations to a laser beam. And then subsequently here, so this depicts the laser beam. This is some 2D sheet. There could be a vortex here symbolizing a black hole. But then what you need to do is you need to do a readout. So this is an interferometric detection scheme. What we did in Nottingham, we developed a global measurement, which we are currently writing up. And we also created a standalone device. And what you can do is you have these fluid interfaces here tested or presented, of course, at room temperatures and pressure. What you use is you have you measure ripples on a fluid interface, and you use the fact that the fluid can use like a cavity, and then with some detection method, you can reconstruct these interfaces to a very high and unprecedented precision. And this system, of course, can be implemented in helium, and this is what we're going to do this year, to simply merge this vortex flow with this novel detection method to go beyond. Okay, so this brings me to the last topic, and I think I need 7 minutes if I'm fast, and then I let you all go to really enjoy a glass of wine. But the title said Black Holes and Early Universe Simulations. And again, here, when we talk about the universe, early universe, we talk about the history of the universe. This is a huge subject. And what I'm interested in is a huge subject, spans over 13.8 billion years. But what I'm interested in are really just the first 10 to the minus 32 seconds. And there's a lot of interesting physics happening. And what is happening? So first, pre-Big Bang, we don't know really what's happening. There are models, such as, for example, the false vacuum decay, that also is being investigated in this UK network program. But so pre-Big Bang, your guess is as good as mine. There is no theory or no established theory. There are models, but there's, of course, no conclusion. Okay, so we believe the Big Bang maybe could also start differently, but let's say it started with a Big Bang. Then it was followed by what we call this inflation. And inflation is this rapid expansion. And how rapid is it? Well, in 10 to the minus 33 second, the universe in size grows by e to the 60, 10 to the 26. Now, what one has to understand is that the general assumption is while these field modes reside on a space-time fabric that changes so drastically, everything can be described with linear perturbation theory. So, and what happens here that the fluctuation gets stretched beyond the Hubble scale, which is the representative time scale. These fluctuations get stretched, and once it's beyond the Hubble scale, these fluctuations, they can't oscillate in time anymore, they freeze. And then these will eventually get converted to density perturbation, and then this density perturbation should be accountable for the large-scale structure of our universe. Okay? So this is a very important thing to explain this inflation to what we see today. It does solve a few problems, but then of course, with inflation it's not quite done. You need to also, when inflation ends, you need to unfreeze these modes and you need to create these particles. So there are a lot of questions, and could one set up an analog experiment where one can see these features? And we haven't done it, but here's the roadmap, and I think it is possible. So and now we need to ask ourselves, how big is a hydrodynamic universe? How big is this air-water interface for the little ripples that live on there? And is it a large or a small one? Well, and the size of this hydrodynamic universe is given by the interface wave speed. How long does this ripple, for example, need to move from one corner to the wine glass to the other one? And this interface speed, they depend on the gravitational acceleration on Earth, so it's 10 meters per second squared. They depend on that. Now what you can do, you can switch on external fields and modify the gravitational acceleration as seen by these ripples. And so that's a proposal with Sebastian together we worked on, where we looked at two things. So one thing that can change acceleration is, of course, a mechanical acceleration. The other thing is you can add an external gradient magnetic field. And what you can do, if you can control these external fields, you can control the acceleration as seen by these interface waves, then you can recreate inflation and preheating in other scenarios in your laboratory. And so how do we do this? This is a superconducting magnet at the University of Nottingham. That's Richard Hill's lab, and he's a collaborator on the project. And so we have this superconducting magnet, creates up to 13.5 Tesla, is a very strong magnetic field. And so you can, I should say, so what we want to do is we send this glass of wine through this bore of the magnet, which here is at room temperature. And so just to say how, so water fluids, this little strawberry here, which is there because you can actually make it levitate because it is a fluid and it's diamagnetic, and diamagnetic materials, they get repulsed from strong magnetic fields and want to move towards weaker magnetic fields. So if you have a gradient magnetic field, you can make things levitate. You can even change the sign of the gravitational force and can turn it around. So there is a point in this magnet where a wine glass upside down would be a stable configuration. And this is what we want to do next. We want to use this to mimic and look into inflation. And I'm almost done, 5 minutes. What we have done is, working towards that, is to understand a bit better these interface waves here. We want to excite these air-water interfaces or these fluid-fluid interfaces through acceleration. So what we have done, we've built a novel accelerating platform, and we created a fluid cell system where we have two fluids, one on top of the other, that don't mix. And we needed two fluids for two reasons. One is we wanted to reduce the surface tension, and the other thing is we wanted to have a closed system, because when you have an open system, the atoms evaporate layer by layer. So the fluid height reduces nanometers per second. And that means your system is changing, and if you want to go for high precision measurements, if your system is changing, of course you can't do that. So I'm almost at the end. So what are we doing? We have built this mass spring system, the shaker, which has a very minimal harmonic distortion. And what you're looking at here, these are two fluids really, but we only plotted the lower one. This is experimental data here, and it shows how it gets accelerated. And we're looking at the excitation on this fluid interface. This really is experimental data, just presented in a nice way. And you see we're shaking the system, excitations are growing, and eventually they get really, really big. And the question is, can we describe that system beyond the linear regime when all these big waves are there and the theory becomes more complicated? So I really have to speed up, but just to say what is actually happening. So you have this shaker, this mass spring system, it creates an acceleration. It starts from 0, ramps up to some value, it oscillates, of course, and then we stop it, and we let the system relax. So there, because of the geometrical confinements here, there is a mode that naturally likes to live in there. And we're looking at how this mode changes in amplitude. And what we're doing, we'll repeat this experiment 1,500 times. And we make sure that the shaker is the same. We make sure that the temperature is minimally changing. And what we're seeing is here, this is in meter, we're looking at the amplitude of this wave. And they are created in pairs for momentum conservation, but we're creating field modes in this fluid cell. And what's happening is, here you can see the orange, the yellow one, that simply is, this is noise of our detection method. So at the moment, not using the interferometric technique, using some other methods we developed, we have a resolution to around, I would say, 10 to the minus 6 meter in the micrometer regime. We see these modes growing as straight lines. It's a log plot, so it means they're growing exponentially. And then what we see is that depending on how much content was there, we're working with the fluctuation in the system as they are, which we are estimating to be of 10 to the minus 9 nanometer. These are the fluctuation content in this system at the beginning. And we see that eventually the signal starts to grow out. It's undergoing parametric resonance. Fouquet analysis predicts this exponential growth. And what we see is that here then when you stop the shaker, of course the system relaxes, it dumps because it's a highly damped system. And what you also see is that some modes start to stop growing long before we switch off the shaker. And that's an indication for nonlinearities in the system. Okay, so, and what we were able to do is or what the next step are, we want to learn about the initial state. When we run simulations for the early universe, you also have to fix your initial state. You have to know what your initial state is. What is the noise content in any system, in your fluid or in superfluid? Then you want to really understand this field theory. And so what we're developing are thermal field theory methods for your fluid interfaces. And in particular, we want to extract the nonlinear field theory. And this is motivated by this really beautiful paper here by Jörg and Sebastian and collaborators. If you read one paper of the papers I talked about today, read this one, it's really beautiful. So and then, of course, we want to link this effective field theory we get to the fundamental hydrodynamics. What is that? Well, I have two coupled Navier-Stokes equations, one set of Navier-Stokes equation for each fluid systems. It's a huge mess, a very difficult system. How can we link the effective field theory we are reconstructing experimentally to the fundamental physics? So how can we actually push our understanding of fluid dynamics? This is what this is about. And how can we add high precision measurements to fluid dynamics because we need them for the simulators, but because also we don't understand fluid dynamics or haven't tested fluid dynamics using all the high-tech we have to a level which I believe is possible. And then, of course, all of this is to map to cosmology. And then what I just want to say, how well could we fit theories, the red to the black one? We were able to extract the effective field theory for this mode and beyond the linear level, and we get a perfect match with adding two more 5 to the 4-ish theories and then without a free parameter. So that's quite promising, but I think much more can be done. And now this brings us to the very end. So there's truth in wine in Vino Veritas, coming back to the theme at the beginning and very much looking forward to a glass of wine. 3 things I have to say. So when you give a talk, it should have some impact. So what should you take home? And I hope that when you go home and when you go next time and drink a glass of wine or look at a glass of water, that you look at it with different eyes. You look at the system as an interesting physical system where you can set up bizarre physics, really. So I hope I have changed your way to look at air-water interfaces or fluid-fluid interfaces. It's also that there is an opportunity of discovery. So remember this stationary draining vortex flows are not well understood. The field theory for interface dynamics, still an open question. But then, of course, also the opportunity to set up this strange physics in the lab. And of course, when you talk about opportunity, there's always a risk-taking. And of course, for some of the things presented today, the question is not if we fail in the sense of not being able to deliver what we said we would, which I'm less worried about, but of course there's always the element of failure. That, you know, you set everything up, you do everything right, but maybe the physics is just not as exciting as you were hoping for. And I think one should always work in a regime where at the boundary of success there is failure. So by pushing hard, by pushing yourself hard, eventually, of course, you will fail. And I think that's a very important part of research. And with that said, just to mention my group, this is my research group, very highly talented young researchers, PhD student postdocs, still hiring. If you're interested to join, just send me an email. And then we were talking about the UK. UK is really a fantastic place for this simulation. So is a 4.2 million investment in this field line of research. There are 7 universities involved, theorists and experimentalists alike. Is a really diverse and excellent scientists working on this. 2 of the people are here today. I mentioned that already, Jörg and Sebastian, who are external collaborators and external partners. Okay, thank you very much.
Silke. Now it's open for questions. You did a big tour de force and I lost some of it.
Okay. We can discuss it over dinner then.
Yeah, I think.
Hi, Daniel.
Sorry. Yeah, so thanks for the beautiful talk. So one aspect of black holes that has been studied, particularly in the past 2 decades or so, is the entanglement properties and the fact that they seem to behave like, you know, the fastest scramblers and the maximally chaotic systems. So I wanted to ask, do you see some chance of addressing this issue? So for instance, testing things like Lyapunov exponents or out of time ordered correlation functions in these analog systems?
So that's a difficult question because so first of all, black hole entropy comes from the dynamics for black holes. So it is not as straightforward.
Sorry, I appreciate that entropy that might be too hard to us, but to see something like the Lyapunov exponent, all you need to be sensitive to is basically the envelope temperature. Sorry, yeah. So I'm not wanting you to test entropy, that might be too hard, but to test things like chaos, all you need to be sensitive to is the the Hawking temperature, the Hawking-Unruh temperature, and this I think you can, in principle, see in some of these analog systems.
So that's an interesting, in principle see, that is for an experimentalist, the challenge.
That's why I'm asking you, can you see it in practice?
I believe the paper I was briefly mentioning, what you want there, if you're talking, for example, local probes, local measurements, so that's what we're trying to set up, Jörg here in Vienna, we in Nottingham, and modeling with Sebastian, how you can get sort of Unruh detectors, how you can add them to the setup. So a quantum simulator is not just controlling and manipulating the background flow, it's also the readout. And so I'm not sure if I can't answer your question directly, maybe we can have more discussions about it.
Sure.
But this is one direction of caring about this. What can you really see? What are you sensitive to? How do you interact with a quantum simulator over in the time domain without destroying it? Right? So this is, I think, one of the most exciting new areas in that field. And I believe it's a matter of time, but it's a very challenging thing. So I think should discuss more later, and also with Jörg, who wants to set them up here.
Okay, thank you.
Another question back there.
So you mentioned quickly that there was some kind of interferometric measurement of basically the waves in the water or liquid helium. I was just thinking that if the refractive index is so low, especially in the superfluid helium, then wouldn't you need a lot of light and heat the helium up above
So a few things. Let me first go back. So we haven't done it in helium. And in helium, of course, you are limited with how much power you can add. Now, if you're just below the transition temperature, you don't need to worry so much about it. But if you go to microkelvin, you really need to worry much more of the energy you're giving into. And it's true, the transfer from the density or the height fluctuations to your laser beam goes with n squared minus 1. So if n is very close to 1, if the refractive index is very small, you have a problem. And so what I just want to say, the system we have had here, and this sort of has a lower refractive index than superfluid helium, helium vapor helium, because we wanted to tune away the surface tension, and as a byproduct you get a refractive index from the interface that is lower than helium vapor helium. So we can do it, but this is a classical system, and we call it sometimes the sun, because you shouldn't be looking into it because we're blasting a lot of energy in it. But have in mind the system, the setup we're using here is a conventional method. Conventional is a bit of a prepped up normal fluid dynamics interface detection scheme. And for the new interferometer, we expect to have a higher precision. It's a different technique. So, long answer, very short. We can see interfaces which have a lower refractive index already. We have set up a method where we believe we can overcome it. It's also depending on how big these ripples are. And you're right. The question is, how much can we push it? How much can we see with the least amount of intensity? And then it becomes to improve the interferometer maximally. So it is a technical challenge, but not an obstacle.
Okay, one more question maybe. So I was thinking about this Hawking radiation, where you have like entangled particles, one going in, one out. Is there some scheme how you could test this with your setup?
So personally, obviously, when you have these configurations we're setting up, one could look at Hawking radiation in 2+1 dimensional space-time geometries. The one case, the one person who has really worked and developed that over the last few years a lot is Jeff Steinhauer, and he looks at 1+1 dimensional effective space-time geometries where you have a black hole horizon. And so now you could say he can see that there is sort of a pair creation process, and now you wonder, how can I show that if I create a pair, that they're not just classically correlated, mean when I see the one, I see the other, how can I show that they're entangled? And so what you would need to do is to do another experiment on top of that, showing this entanglement, continuous field, continuous variable entanglement in this setup. Jeff makes arguments based on occupation numbers, which we can be discussing about, which look very promising, but one really should measure non-commuting variables, features. One should really show, I feel that there's another experiment necessary to really fully convince yourself that these modes are indeed entangled. So people are working towards it, but it's a hard problem, and it, in my opinion, still room for more.
Further questions, comments? Is there something from the outside? No. I was wondering one thing. So, in this shaking of the superfluid interface, how does that,
fluid,
of this fluid interface, how does that map to inflation? I mean, I don't know if you want to explain to your grandmother how does the shaking of the fluid interface
So the
maps to
shaking is a
inflation?
different, so for really getting inflation, you would need some strong external gradient magnetic field, so which you tune the magnetic field in a certain way, or you move your sample through the bore of the superconducting magnet. So you would need more than that. These parametric resonance experiments are twofold interesting. The one is it allows us to study the effective field theory and to get a better understanding of that, following very much what you have done, basically. To say, look, this is my field theory. This is my linear term. These are my nonlinear terms. This is my simulator. Now, parametric resonance could perhaps be linked to preheating. That's what we're trying to find out at the moment. So maybe you can sort of use that already for some cosmological insights. What is interesting here is, if I compare this system to what you do, is that you have this wonderful field theories, like weakly interacting Bose gas, and you have this nice, let me put there, a very good grasp and a very pristine and nice theoretical model because of this weakly interacting system you're dealing with. This system are strongly interacting, highly damped, so to see some of the cosmology effects in there would mean quite a lot. Can you actually use this and extend all of the simple models to strongly interacting field theories? So that's something that we can't even calculate partially. And so this is also what the simulators are about, to see how much our theory models are a stretch, and can they survive in this non-ideal experimental setup.
So, I mean, so really to look at inflation, you have to make an expanding.
You have to okay, so coming back.
So what you do is basically,
okay, no, I
if
can
translate
explain
it correctly, you change the sound velocity.
So in our case, interface. I did mention it briefly at the beginning. Let me go back to the slide. So what you need to do, you need to control the perturbation speed. So in your system, you would change the interaction strengths of your bosons, your atoms, and here in our case, we use this external fields, gradient magnetic field, to change chi, the effective gravity, right? So that's why you can levitate things. You can even remove gravity completely, tune it to zero. So you would start from, I don't have the picture here, I can show you later. You would start with the gravity felt by these interface waves, 10 meters per second squared. You go into the spore of the magnet, and where sort of when you go in and where this strawberry is levitating is where the magnetic field, this acceleration is effectively zero. And so you tune then the propagation speed, which is proportional to this chi effective, from 10 to 0. And the way you go to 0, you can then change it over several orders of magnitude. We estimated we can get a change in the size of the analog system with this superconducting magnet that we have by a factor of 50,000. That's enough to see certain modes undergoing this mode freezing. So, having said that, all we needed to do as well, we needed to understand the field theory. Now we know the field theory, now we can go back and then we can do the experiments. We should be able to see mode freezing in this setup.
Okay, are there other questions, comments? Otherwise, I think we should thank Silke and everybody. So which wine were you picturing?
Sorry?
Which wine were you thinking of?
Which wine? Well, any wine today.
It was red wine, or?
Red wine. Anyone does.
You should have done it with grüner Veltliner. Or with gemischter Satz.
Sorry. Yeah. Foreigners.
Yeah. Okay. Well, thanks. And due to